All right, so let's look at this magical number that's going to tell us how strong our relationships are. It's called the linear correlation coefficient, or the Pearson product moment correlation coefficient, if I remember that right. It has this lovely formula here that you can pretty much ignore because we're not going to do it by hand. But you can look at it for a second and realize that what it is it's the z-scores. That's a z-score formula for x times the z-scores for y, and you multiply them. So how many standard deviations away is your x? How many standard deviations is y? Multiply it, and then you do it again and again and again, and you add them all up for all your data points, and you divide by n minus 1. There's that n minus 1 thing again, called the degrees of freedom. All right, so put another way, that correlation coefficient, it's sometimes capital R, sometimes lowercase r, depends on your book, tells us whether we can know anything about the scores on one variable if we already know the scores on a second variable. In other words, it tells us the relationship that's going on. Now, the linear correlation coefficient has a whole bunch of properties. Let's look at them. That is always a number between -1 and 1 inclusive, meaning the lowest it can ever be is -1. That's called a perfect negative linear relation. The highest it can ever be is +1. That's called a perfect positive linear relation. The closer it is to 1, the stronger the evidence of a positive association. The closer to -1, the stronger the evidence of a negative association. In other words, the bigger the number is in magnitude, the better. If r is close to 0, that implies no linear relation. Now, be careful, because that doesn't mean that there's no relation, just no linear relation. It might be like a parabola shape or something. Let's see, there's no units to it. R has no units, and it is not resistant because, well, look how it's made. It's made with the means for x and the means for y, and remember, mean is not resistant either. So since mean isn't resistant, standard deviation isn't resistant, so neither can R be resistant. All right, now this is just a rule of thumb. Notice this is not perfect, but this is just kind of our way of gauging this. Let's see, -1 is less than or equal to R, which is less than or equal to -0.8. That's considered, I guess I don't really like the word very in there. I'm just going to say a strong negative linear relation. And then between 0.8 and 1 would be a strong positive strong positive linear relationship. Between it's really -0.7999999, right? Forever. Matter of fact, hold on one second. Let me put a little repeater bar over there. There we go. So -0.79 up to -0.5, we're going to call a moderate, actually again, moderately strong or just moderate. Moderate gets used a lot. Or moderate negative linear relationship. And then between 0.5 and 0.7999999, that's a moderately strong or moderate positive linear relationship. And then being lower than 0.49, and again, those are 0.49 repeating one. That's a weak relationship or possibly no relationship, depending on how bad it is. All right, so let's look at some graphs. This is how linear correlation coefficient rolls. So if you look at the top ones, you can see here's +1. See how the line is the dots are perfectly in a line? And then here's 0.8, a little bit less perfect, right? That's a strong relationship, but just barely. Then you got this weak relationship at 0.4, really weak relationship at 0. Then these are -0.4, negative weak. Here's negative strong, right? -0.8, and then there's 1, -1, a perfect relationship. Now, what you don't want to start thinking is oh, because the correlation coefficient is 1, that means that the slope was 1. But that's not the case, right? The slope could be all sorts of things. So, for example, I've got 3 values right here. These are all with a correlation coefficient of 1, but they're at very different slopes. This one's steep, this one's kind of moderately steep, that one's pretty shallow, and so on. These ones over here are -1, okay? I don't want to get into that one in the middle because it causes things to go haywire because it has a 0 slope. And these guys all down here would all have zeros, but they have relationships. They're just not linear. Like that's a 4th degree polynomial relationship. That's a hyperbola over here, okay? we're not going to really see those very much, but the important point to realize is that just because it has a 0 does not mean that it's no relation. It just isn't linear, which is what we care about for our purposes. All right, so now you're going to take the values up here, which I've given you, and you're going to match them to their graphs down here. So take a moment, look at it. I will pause you and put in the right values. All right, let's see if you match me. So I said that this one up here was 0.85. This one over here is negative 0.94. This one here is 1. This one's negative 0.54. Let's see, this one here is 0.42. This one's negative 0.33. This one's 0.17, and this is negative 1. Okay, so the obvious ones are the 1 and negative 1, hopefully, right? So they're all in a line, everything's perfect. That's 1, that's negative 1, okay? So you'll notice that I put all the negative ones on the right side, so let's compare them. This one is obviously 0.94. See how tightly packed those numbers are, those dots, excuse me, are around that line? That's the strongest of these relationships, so you have to go with the biggest number, which is negative 0.94. And that leads you to these two right here. And they're both pretty terrible in their own right. But I gauged that this one up here for letter D has the points just a little bit more clustered around that line, whereas this is kind of more all over the place, right? It's a judgment call, I know, but these points looked a little bit more all over the place, and this one looked a little bit more in tune. So I went for negative 0.54 for this one, and then negative 0.33 for F. I think it's a little bit clearer on the positive side because the weakest ones are these two, and this one for G is just awful. I mean, these points are making like a circle. It's such a terrible thing. It has to be 0.17. I mean, yeah, it drew a line in it, but like if you didn't have that line, it would just look like a big circle of dots, right? And here, this one's not that great either, but they are kind of clustering a little bit around that line, so that's 0.42. So hopefully you're getting that, you know, the highest it could ever be is 1, the lowest it could ever be is negative 1, and the ones that are on the edges, the negative 0.94 and the positive 0.85, those are the good ones. Those are the ones where it looks like the dots are kind of clustering around the line. Those are strong relationships. Okay. The closer you get to 0 in the middle, the worse it is. The harder it gets to be to gauge what the heck is going on. All right. So now we're going to have to compute the linear correlation coefficient. And we're not going to do it by hand. We're going to use our computer programs. So let me grab this data. And of course, you might not have this data in an Excel format, so you're going to have to type them in your own self. But let me go here and let me, oops, you know what, let me type these in. I should have grabbed the % reading score thing, so let me grab that. That way I've got some labels here. All right. So there's the % on free reduced lunch. There's a % that passed that math test. Beautiful. All right, now I'm going to do this a couple ways. Oh, but first, before I do anything else, I'm going to save this, and I'll put it on my desktop. But this is Chapter 4, Technology, right? That way, you can put your last name in it too if you like Smith or Johns or whatever your last name is. But that way you save it, and that way when you're ready to email it or upload it, if that's an assignment for your course, then you'll be ready to do that. Okay, now how do I do this? Well, there's a couple ways in Excel. However, the method in Excel, let me put it right here, correlation coefficient. So Excel will do this, and we're going to do this in StatCrunch. Personally, I very much prefer StatCrunch for this, but we're going to do it in Excel as well. Okay, now the way to do it in Excel is there's actually a formula. Equals correl. And then you say, okay, what's your first array of data? That's these data points from A2 to A14 for me. And then my second array is B2 to B14 for me. Close my parentheses. And oops, don't type an apostrophe at the end of that. Yes, I know I have an error. Delete it, enter. And there you go. There's your correlation coefficient. Okay, now with StatCrunch, let's get this open. So I'm going to copy. I'm going to go to StatCrunch. Oops, I'm on my upload page for my website. There we go. Okay, so I'm in StatCrunch. I'm going to open StatCrunch and go here. Click on variable 1 and kind of paste that in. And let's see, where is it? All right, so we go to Stat. We go to Regression. Pick Simple Linear. Click on that. What's your X column? For me, it's free reduced lunch. Y column is passing math. Next. We don't have to worry about this. This is actually chapter 14, and we're not going to cover that, so just ignore it and say next. Again, we're not going to do much for this yet. We can do some of the stuff later on in the chapter if we so choose, but I'm not really interested, so I'm going to click next. Do I want it to do a plot? Right? Yeah, it might not be bad if you want to have a plot of it. Knock yourself out. Residual plot, we'll talk about that later. That's coming up in section 4.3, so we'll come back to this, but you can turn on some of these if you want. It's this one I think that we like the most, residuals versus x values, but we're not going to do that. And then graph layout, that's fine. Calculate. All right, so it actually has produced a whole bunch of stuff. I don't know if you can see it all, so you can make your window bigger. So there it is. It's a whole big mishmash. But do you see right here, it says R correlation coefficient. See that? There's your correlation coefficient. And it gave us a whole bunch of other stuff that we're going to use later. But there's the one that we're interested in. So I can go to copy. And then I can go back to my Excel spreadsheet. And I can right click and paste. Right? And there it is. See, it just copied what I was highlighting. Isn't that nice? Now, if you don't want to do that and you want to copy the whole thing, let me see. Copy. Let's see if it does it. It might not like me because I copied that one thing that one time. There it is. There's the whole kit and caboodle. Right? And then you can see the correlation coefficients right there. So you can highlight it, bold it, make it obvious. Cool. Let's not do it that way with just the copying of the one thing because it makes it hard to gauge what was done. So copy the whole kit and caboodle and put it all in there. I just wanted to clean up my data there. All right, cool. And I don't know if you noticed, but we told it to do a plot. Do you see down here at the bottom it says next? If you click next, there's a scatter plot of that data and the line graphed on it. And you can copy that as well. You're going to want to anyway for later data sets. You might as well know how. And that's how. So you can copy and paste a plot in if you like. All right. So we found the correlation coefficient. We now know how to find it. You do not want to do this by hand, right? You're going to make Excel or StatCrunch do it. All right. So where's back? There it is. So it's R is equal to negative 0.687, if I'm not mistaken. Oh, Excel. Yep, 6879. Let's put it that way. 6879. Okay. And again, capital R, lowercase r, doesn't really matter. But there you go. And you can tell yourself, you know, done with Excel and StatCrunch. All right, now what type of relationship does that appear to be? Well, 0.68 figures into our table here. It's a moderate negative linear relationship, or moderately strong negative linear relationship. Moderate, strong, negative. Oh, my dog is barking. All right, this implies that schools that have higher rates of students on free reduced lunch have lower pass rates on the math tests, which makes a lot of sense, right? If you have children that are poor enough to not know where their next meal is coming from, so that they need free reduced lunch, then they probably don't have the time or energy or perhaps parental involvement to study math. You know, their parents are working jobs trying to provide. They're not going to be able to study math and do well in those math tests. All right, I'll see you here next time for moving on to more scatter plots. See you then.